very much for introducing me. The study which I would like to show here is a long-term study which was done by many people, which are named at the slide. And it's basically the study made by the employees of Charles University in Prague, Czech Academy of Sciences, and also researchers from Brigham Young University. And the talk will be focused on the origin of forms which we all know, all of us. We know that in sandstone regions there are spectacular landforms like the arches or pages, the overhangs, pillars, and pedestal rocks, and also the other forms. It is generally claimed that these forms are a result of weathering and erosion, but there is maybe something involved behind what we can easily see, because the erosion and weathering could be easily seen, but maybe there are some important issues hidden behind these processes. We can get closer to these things when we ask questions like, how can these forms have so perfect shape? Like the sandstone ridges are often very smooth on the surface, and you can see they are arching over the tens of meters. How can be erosion and weathering, as they occur in very shallow zone? How can create randomly such a nice shape if they are not controlled by some process? So what coordinates the erosion and weathering? We know very nicely balanced pedestal rocks, where the rock is sitting on very narrow stem, and you can see only this rock, and there is nothing, just the sand as there. How is it possible that during each time in evolution of this rock, there was no time when the rock was undercutting the center of gravity, that the rock doesn't fail into the sun? These are somehow wonders, and that's the reason why we are so much interested in these arches, but why there are so many national parks globally on sandstone. So the purpose of this talk will be to show, to demonstrate the effect of gravity-induced stress on erosion and weathering and the evolution of these landforms. By gravity-induced stress, I mean the pressure inside the rock, the pressure between individual grains of sand in the sandstones, which is in any rock, because any rock on the Earth is in the Earth's gravity field. It has some weight, and the weight of the overburden necessarily means the pressure inside. We use basically three types of methods. Most importantly, the physical modeling with a special material is with weak sandstone, or better say lock sand. I will show it later. Then we use the salt and frost weathering experiments with cemented sandstones from US and Czech Republic. And last but not least, we use the geotechnical code fluxes for calculating the stress inside the landforms. And the material we use is from one quarry in Czech Republic. It's a quartz. It's called weak quartz sandstone, but in fact it's a lock sand, because this material has no cement. And what is interesting in the quarry, you can see on quarry faces which are few months old, or a few days old even. You can see nice arches and these small overhangs, small scale. Each time the scale is 10 centimeter large. So small scale features which are created extremely quickly, within hours or days, after exposure by rain and other processes. And so this material is reacting very quickly, and it creates the form very quickly. And interesting is that the same forms we can find on natural outgrowths of this sandstone. So this lock sand is basically a sand which was sitting 60 million years, the grains one or the other, under the pressure. So the grains which randomly settled at the places of contact, they dissolve a little bit and are precipitated. So nowadays the grains have small indentations. So they fit a little bit one to the other. And that's actually the reason for its exceptional behavior. Second reason is that this material has no cement. So, and it has very strange properties. When they were mining this material in the past, they used the water. They just used pressurized water, and the water was removing the material easily. Then they became dry mining, and they cannot use even the strongest excavators. They have to first blast the material by explosive because the excavator was not strong enough to scrap it. So this material decays in standing water spontaneously, and in the same time you cannot use the excavator to scrap it because it's too thin. These strange properties can be demonstrated on a short video where you can see a 15 centimeter cube of this material. You can easily prepare a cube of that, and you can see that the cube can withstand the load of car. It's a sand. There is no cement in it. And you take it and you put it to the water. And this is roughly 3 times faster than it goes in reality. It disappears. So it withstands a car. It doesn't withstand a still water. Now, the reason why it withstands the car load is simple. The material is interlocked, so to slide the material, you have to crash the quartz indentations of grains. It will never slide until the crashing. So the compressive strength is 3 megapascals, relatively large. It can keep 30 meters high faces for thousands of years outside of mine, this material. But tensional strength is 10,000 times smaller. You cannot even lift it, a small cube, by your hand because it will immediately crash. So because of the interpenetrative fabric, it's firm for the compression. Because of lack of cement, it's weak for tension. But there is one thing missing in the explanation. Why the still water disrupts this material? The reason is process called slaking. The slaking is process where you put this material into the water, and the water rushes into that, partly due to the capillary forces. The water wants to touch the quartz grains, so it sucks into it. And sometimes it's encircling the air in force. And the small capillary force, few kilopascals only, is strong enough to pressurize the air for a few kilopascals. And the pressure of the air is acting against the pore walls, and it's disrupting the structure from the inside. And once the structure fails, the material fails as well. You will see the demonstration on the next one. Just to make some comparison, we can compare it with the dry brick wall. If we had a dry brick wall with no mortar, we have basically the same material only in 1D dimension. And we can easily put out the brick on the top of the wall, easily, any person. But if the wall will be high enough, no person is strong enough to take the brick from the bottom because there is big friction. So that's basically how it works. The pressure inside the material is similar like the tension from outside. And now there will be a demonstration what happens if we take similar cube, 10 centimeters in size, which is loaded from the top by very small load, just by half a kilo. And we will in steps unload this material. And you will see what will happen. The red arrow, which will be here, will show the unloading steps. So you can see the cube. Immediately once we flood it, the pillar is formed there. You can see the angle of repose of normal sand, but the lock sand keeps vertical wall underwater. And now the form will be stable for months, for years, forever. Once we unload, immediately the erosion will restart. And we can keep with that. We can play with the erosion as by making the pressure lower, as the cut can play with mobs. What it means, the erosion is completely controlled by the stress. And when we remove the stress, it is gone. The form disappears. Now, very similar experiment, seemingly. We have two bases and one top loading. We have similar shape of the material. It could be easily cubed. And see what will happen. We have two bases, not just one base. And instead of pillar, there is the arch. So what this shows, it shows that it's the stress field what fully controls the erosion. If the stress, the pressure inside there cannot jump across the free space. If it can, then the things could fly, levitate. And as such, the stress has to go into the buttresses. And as there is nothing, it must create the arch or two pillars. The arch will be there in case that there is enough weight of the mass itself, sand mass itself. If there will be low amount of mass, it will be two pillars instead of arch. So these are the experiments, and we did many other experiments which basically showed that to create the arch, you only need to have a discontinuity, either horizontal or inclined. And it is very nicely visible at this slide, which shows the results of numerical modeling of the stress. Imagine a break of this shape, which you cut across in the middle. So this is the discontinuity. It could be 1 millimeter thick only, the discontinuity. The stress cannot pass across, so the stress instead goes around and creates high stress arch. Whatever is in red, it's high stress. Whatever is in blue is a low stress. And you have low stress zone here, low stress zone here, and low stress stress shadow here. So if you have such a brick and you cut it in the middle, you immediately create the arch, but the arch is not visible. But the arch is there. And if the material will be sensitive for stress, the arch will be created from such a shape. You can see that to enlarge the arch, this is experiment where the material is wrapped in foil to somehow create a more to situation which is similar if the material will be in the muscle. To enlarge the arch, you only need to cut these indentations, and immediately the stress shadow will be created here. And once you flood this material again, you will create a bigger arch. That's how it works often. You have a small horizon, clay horizon, which is keeping eroding, and therefore the whole form is keeping to be enlarged. Overhang is basically very similar form to arch, except the discontinuity doesn't go across the muscle, it dies out in the muscle. So that it doesn't create the arch, but the half dome, say, or what to call it. So after flooding this discontinuity, you have a nice alcove or overhang there. Well, these experiments were done by slaking, which is a strange process. No one expects that the material will be flooded or something. And it's made on small piece of material in the block. But this experiment is done on the quarry itself. And it's done by watering can. You apply a watering can, then you make a photographs, apply another watering can, make another photographs, and from these photographs there is a video. So each photograph, actually, each video frame is a same amount of water applied on the form and potentially the same erosion. And have a look what will happen. Here is the discontinuity made by drilling across this material. And you can see an ugly shape on the beginning, and you can see how it slowly but surely becomes very nice arch, and then suddenly the arch is gone. I will let it go once again, just to see how the shape is making nicer and nicer, because the erosion of those parts which are ballast is faster than those parts which bear the load. Because the load-bearing parts are under stress, the ballast is eroded quickly. And now the horizontal arch, which is one of the last things which was. So this is one of the best arches which was developed by my students in last month. And you can see that at the beginning it was an ugly rectangular block, but I will do it once again. But at the end there is a very nice and smooth arch which is not far from the landscape arch, for instance. And you can see that the erosion sometimes cuts on some place, sometimes on the other. And finally you have a very nice shape form. So this demonstration shows that it doesn't matter much about the shape at the beginning, it matters more about the stress field inside her. Well, this is another example. In this case, the block was put on the roof of the building, sandstone, this rock sand block, and was left there for 2 years. And you can see how the stress modeling predicts exactly what will happen. If you make a stress model of this block, you can see that there is an arch somehow diffused, low stress here, low stress on the bottom center part of the side and the corners. Exactly what the numerical modeling predicts that happens. First, erosion is on the corners, at the top and at the middle. And finally, after 2 years, you have the arch. No one touched the arch. It's just the natural rain, natural sun, and natural frost what shaping within 2 years. So this material inevitably creates the landforms, whether you wish or not. And that's not just the arches. This is another example where it was prepared a discontinuity which is discontinuous, which is also common. There is the sand at the beginning placed into the discontinuity, but it will be, within a few seconds, it will be nicely visible. Oh. And you can see that the shallow discontinuity propagates, the erosion propagates up and down and creates very nice, these hourglass pillars. And you can even see the stress lines there. They are visible. You can see how the stress, likely speaking, passes across there. So even a very shallow discontinuity creates a large space because it creates stress shadow around the discontinuity. But the nature is complex, so the discontinuity as we see is not actually always the discontinuity as the stress is applicable for the stress. Very surprising experiment was this one where we created this pillar. We tested that it will not decay underwater, and then we tried to drill a hole across. And accidentally, during the drilling, we crashed the block into 2 pieces. What we expected, obviously, was that the erosion in next flooding will cut across and destroy the fort. But what happened was that this block was crashed into 2 pieces which doesn't move one to the other. So the indentations of the grains were still preserved. From one side of this continuity, the grains were still fitting to the other. And what happened instead when we put out this lead load from the top and we put a smaller load on it, the erosion doesn't go along this discontinuous surface, but it cuts up and down and finally created these pillars. These pillars are from material which is cut it in the middle. No man is able to just lift it in the hand. It will immediately decay. So it's extremely fragile, but it's still there because of the loading from the top. And the discontinuity is not even easily visible there. And we have a very nice example in the nature. In Wadi Rum in Jordan, there is the Burda bridge. That's the bridge which spans across the heavily jointed zone. So there is blocks of sandstone originally like this. You can see the joints on the arch, it's enlarged. And see that note that there is the erosion cuts, or the weathering, cuts the form independently on the joints. Each block which is separated by the joint is actually eroded in the same way because the stress is going across, so it keeps stable the surface. And all other part of the jointed zone is eroded away already. So some joints are separating the material and separating the stress field, but there are joints which we can easily see which doesn't do that. Not each joint is a boundary condition for the stress field. And maybe the most strange experiment was one of the first we did. This is a rectangular block of sandstone. We put 18 kilograms of load on it. Then we flood it first time. Then we put one load out, flood it second time, third time, and finally flood it to here and here. And that's the result. This form has 2 by 3 centimeters the stem and 100 times larger the cup. This is similar to most crazy natural wonders we have. This was one experiment. It was not like that we did 1,000 experiments and this is the only which fits. That's the first, and we actually have no reason to do other experiments. Why this is possible? Because what the erosion do, it goes obviously from different sides. No material is so homogeneous that the velocity of the erosion will be the same from all sides. So what it does, it goes faster from one side, slower from other. But then when it gets closer and closer to the center line, it's slower and slower. And that's the only chance how you can get close to the center line from each side in the similar time. So obviously it's not easy to create such a form in the nature, but this process strongly helps for them because it tends to not undermine the center line. So what it actually means? It means that all these different forms, the arches, ridges, the alcoves, the pedestal rocks, pillars, all can be explained by a very single mechanism, that the stress field is fully controlling the erosion. And what actually happens in the sandstone landscape is that the load-bearing portion of sandstone mass are eroded slowly, and therefore they are preserved. And the major sandstone landscape is made of these forms. On the other hand, not loaded parts, the ballast, is rapidly eroded away, which has 2 consequences. First, the forms are nice, and second, the ballast will normally tilt or will create failure of the form. Arch, for instance, very narrow, is very weak to fall to the side. But this doesn't happen because the ballast goes quickly away. You should not think on these sandstone wonders as about a stupid piece of rock. Because what the stress actually do, the stress interconnects billions of grains in the form into a single system. If you change anything in the landform, the whole form will be informed through the stress field, and the erosion will be somehow different on its surface. What is critical for shaping these landforms are the discontinuities in the massive, where the stress cannot pass across, and as we have and planar discontinuities often create the curved shapes of the stress field. And that's the reason why we have so many curved shapes in the sandstones, because we have many planar discontinuities which force the stress to go in curved shape around. So the planar discontinuities makes curved shapes. And what is interesting, very shallow discontinuity is able to, due to stress shadow, to undermine the sandstone well above, even tens of meters above the discontinuity. So if you see a sandstone which is eroded more, and the sandstone which is eroded less, it doesn't mean that this sandstone is weaker and this is firmer. It could be because of the discontinuities which force the sandstone for erosion. There's another demonstration where we did a small cut into the sandstone, and you can see that the homogeneous sandstone will be eroded accordingly. So the small cut will be smoothened into a nice curved shape, and you can see that the discontinuity fully controls actually the final shape. So the discontinuities are extremely important. All what you saw was just some crazy log sand from Czech Republic. There are many such log sands over the globe, and many big sandstones are actually log sands. But most of the landforms are in firm cemented sandstone. So does it work also in the cemented sandstone, or it's something which is special for log sand? There are done experiments with salt and frost weathering. We use basically C cubes which were not loaded, just freestanding cubes, and C cubes from each material were loaded in this frame by a momentum screwdriver to load of tens of meters of overburden. And here is a comparison of different materials from Czech Republic, mainly the quartz sandstones, and some materials from US. The Navajo, Estrada, and Wingate, and others. And you can see that especially the quartz materials, they show much faster disintegration rate for the free-standing cubes compared to the loaded cubes. So, especially for quartz materials, it is much slower erosion if you compress the material. This is the result of salt weathering. You can see nice pillars, similar like those created by the erosion. So the salt weathering creates similar shapes. And frost weathering gives similar result. You have much faster decay of unconfined cubes, loaded ones, compared to loaded cubes. So it seems that the stress affects many different processes. There is also first study made on full scale, because all these were just small models, few centimeters size, few decimeters. So this is from overhanging rock in Pilsen area in Czech Republic, where there is an extremely fast decay. You normally cannot measure the erosion rate, but there is a wastewater coming to this alcove or overhang, and the decay rate is up to 30 millimeters per year. So we placed the plastic bags there, and we measured how quickly the side of the sandstone is receding. And then the photographs were done, the 3D model was created, and the calculation of the stress field was created in this model. And you can see a cross section. You can see that where the colors are hot, it means the stress is relatively high. You have very low erosion, less than 4 millimeters per year. But where the colors are cold, it means low stress or even the tension, the erosion rate is very fast. So the stress controls the erosion also in larger scale. And now there is a question. What creates the landform shapes? Is it the erosion and weathering, or is it the stress field? To answer this question, we could use an analog, like what created the statue of David? Was it chisel, or was it Michelangelo? And the question seems to be crazy, but it's not. Michelangelo, as a man, has no chance to carve anything in the marble. There's absolutely no chance. As the stress itself has no chance to carve anything. Michelangelo desperately needed some tool. So it's not actually his work fully. He has to have something. But the point is that he can use the chisel, he can use the hammer drill, he can use whatever if it will be in his time. And he will create a very similar statue. Because it's a sculptor who defines the shape. On the other hand, imagine a man, even the best sculptor, even the Michelangelo, which you will blind him by a scarf, and you will not let him to touch the rock itself. He cannot create anything nice because there is no feedback between him and the existing shape. So if you apply this approach, then we should admit that the stress field is actually the author of these natural statues. And the erosion and weathering are just tools. And it's very similar actually. Like the sculptor can create the same form with different tools, so can these processes, those stress fields. Obviously, it's not just these several forms which is affected by these processes. The stress obviously affects the weathering and erosion of many sandstones in general, and you can see it nicely in Petra World Heritage Site in Jordan, where we have originally we had nice rectangular shapes, and over 2 millennia these forms were shaped into such shapes, into much more natural ones. When the material from Petra was tested, it was shown that the pressure, how you pressurize these cubes, it affects the erosion rate. The higher the pressure, the lower the erosion rate. And so this probably affects also the cultural heritage, but no one so far cares about the effect of stress on the weather. It is generally believed that if you have too high stress, the material will fail, which is definitely true. But no one before studied the stresses which were 2 or 3 orders of magnitude lower, because no one believed that it could have any effect. But this shows that actually the low stresses at the surface could be very important in weathering, and not only for creating these special landforms. So, last video from the talk will show the very simplified Petra tombs, not so nice as those made by the builders, much more smaller, but it keeps the most important things like the rectangular shapes at the beginning, and you will see that the shape of this form will be quite similar to these old tombs which are in Petra at the final. And you will see that the pillars are there for a long time until they lost loading and they are quickly gone. Exactly what we can see in Petra in many places. So you can see the erosion, you can see how the erosion went over 2 millennia in Petra by this approach. So the lock sand give us incredible possibilities to model things which were beyond any imagination in the past. So, is it a sandstone, some special material, the only material on the earth which do this, or it's more common? Well, the sandstone is special from one reason. Most of the sandstones, and especially sandstones which build these forms, is made of quartz. And quartz is very firm. Mechanically, it weathers uneasily. But it has another special property which most of the minerals do. The quartz, if it's if it's sitting one quartz grains on the other for a long time, due to pressure solution, it is dissolved and it creates these nice indentations. So that makes the quartz special and best for these things. But we believe that actually any landform, any material which has interlock structure, so the grains or blocks fits one to the other, and which disintegrates into these grains or blocks, can create similar shapes. And it fits with the observations in the nature. In Pilot Valley there is a breccia, or heavily fractured dolomite, which disintegrates into the pieces, and the disintegrated material obviously is able to survive in the sealing of overhang, but any material sticking out is eroded. So the breccia is one of the materials which create this. The nodular limestone is made of firm pieces of limestone coated by a clay which easily weathers. Here you also have a nice shapes which might pretend to be a sandstone, because all the nodules which are not interlocked with the others fail off. So the material behaves in similar way. But the best material after the sandstone is probably the granite, deeply weathered granite. You probably know the material which you can even grab your hand, is so much better. And in such material, you have pieces which are still interlocked, the crystals, which, however, whenever they stick too much out, they will fail off. So you have nice blind arch in this material. And maybe some other materials, maybe it's just some random shape in the ice. So I arrived to the end of the presentation. So these sandstone landforms were, to our knowledge, for the first time created by physical modeling, and they are similar to those which you can see in nature. So it's probably one of the best proofs in geology, if you are able to create a form, fully replicate the process, that it could be real. It's not just some chance. The increased stress is capable to decrease the salt and frost weathering, and it's completely able to cease the erosion by rain or flowing water or slaking. And that's actually the reason, we believe, for existence and creation of the spectacular landforms. There is a negative feedback between the stress and erosion. As the erosion cuts deeper into the pillar, the stress is rising because the weight from the organ is still the same. So that due to this feedback, the erosion is diminished in many forms, and the forms could be more stable. And the control of the stress on the erosion and weathering is what we believe the defining principle for sandstone landscape. Because so far there was no definition. You can define sandstone landscape as a landscape where we have these and these and these forms. Now we can see the process which is behind it. Whenever the stress will fully control the erosion, you can expect these forms. So that's, say, process-based definition. And we believe that the stress should be considered in any study concerning the weathering of the sandstone, because it was demonstrated that it could have a strong effect not only in natural forms, but also in case of artificially made forms. There are some papers written on this topic, and I would like to thank you for the attention and thank all the people numerous people which helped with this study. And I am very grateful for Alan and to get possibility to work here, because this study will probably not launched if we cannot